While often overlooked, unless you drive an electric car, there is likely a seemingly humble metal can attached to your exhaust pipe that is an absolutely incredible piece of chemical engineering, a product of a Herculean but now largely forgotten feat of politics and industrial research and development that some scholars have compared to the Apollo program. This is the fascinating story of the catalytic converter, perhaps the most underrated automotive component of all time. Catalytic converters are designed to reduce an engine's emissions by converting harmful exhaust products like unburned hydrocarbons, carbon monoxide, and nitrogen oxides into more benign compounds like carbon dioxide, nitrogen, and water vapor. As the name suggests, this is done through the use of a catalyst, a substance which speeds up the rate of a chemical reaction but takes no part in the reaction itself. Catalysts work by allowing reaction pathways with lower activation energies, reducing the energy barrier required for a reaction to take place. For example, a catalyst may absorb the reactants onto its surface, making it easier for them to bond, or may form intermediate compounds with the reactants that can more easily react with one another. In either case, at the end of the reaction, the catalyst is left unaltered, allowing it to be reused almost indefinitely. Older catalytic converters are known as two-way models, as they only catalyze two oxidation reactions. First, they break down unburned hydrocarbons into hydrogen, carbon, and oxygen, then recombine these elements into carbon dioxide and water. And second, they convert carbon monoxide into carbon dioxide. The year 1981, however, saw the introduction of three-way converters, which can also catalyze reduction reactions, converting nitric oxide and nitrogen dioxide, precursors to photochemical smog and acid rain, into harmless nitrogen gas. While catalytic converters did not begin appearing on cars until the mid-1970s, the technology is significantly older. As early as 1909, just a year after the introduction of the Ford Model T, French chemist Michel Frankel gave a speech at the 7th International Congress on Applied Chemistry in London in which he proposed, quote, supplementary combustion in the exhaust box with the aid of a catalytic agent in order to help reduce future emissions from these newfangled automobiles. While this proposal was certainly prophetic, at the time air pollution was nothing new. Indeed, London's infamous pea soup fog was not actually fog, but rather a noxious smog resulting from the burning of coal, which could, and often did, prove lethal when inhaled. Coal smog became such an issue in the UK that in 1845 Parliament passed the Railway Clauses Consolidation Act, one of the first pieces of legislation in history to regulate transport emissions. However, the true father of the modern catalytic converter was another Frenchman, a mechanical and chemical engineer named Eugène Jules Audry. Audry was born in 1892 in Damont in France, son of a French steelmaking family. He studied engineering at Paris's École d'Art et Métiers, graduating top of his class and receiving a gold medal from the government before joining his family's steel firm in 1911. With the outbreak of the First World War, Audry joined the French army, serving first in the artillery and later France's first tank company. During the Second Battle of the Aisne in 1917, Audry was seriously wounded while trying to repair his tank under heavy fire, an action for which he was awarded the Croix de Guerre and the Legion of Honor. After the war, Audry returned to the family firm and took up auto racing as a hobby, driving a Bugatti race car in his spare time. His obsession with increasing engine performance eventually led him to develop the catalytic cracking process for refining crude oil and coal into high-performance automotive fuel. This process was far more efficient than the older thermal cracking process and promised to meet the increasing demands of the ever-expanding automotive industry. In 1927, with the support of the French government, Audry built a pilot catalytic refinery in Saint-Julien-de-Pérolas. Unfortunately, though, the plant's output was far lower than expected, and unable to secure further support from the government or industry, Audry moved to the United States, settling in Paulsboro, New Jersey in 1930. Here, he worked with Saucony Vacuum and Sun Oil to develop improved versions of his catalytic process, with the first full-scale refinery opening in Marcus Hook in Pennsylvania in 1937. By 1942, 14 Audry units were operating across the United States, producing large quantities of high-octane aviation fuel, which proved decisive in the final Allied victory in the Second World War. After the war, Audry turned his attention to another problem: air pollution, which even in the 1940s was becoming a serious problem in commuter-heavy cities like Detroit and Los Angeles. Though the link was as yet unproven, Audry suspected that automobile emissions were responsible for a recent spike in lung cancer rates, and he set out to invent a device to clean up exhaust gases. In 1948, he formed a company called Oxy Catalyst Inc. in Wayne, Pennsylvania, establishing a laboratory and office in a converted ballroom and horse stable. Within 2 years, Udry developed a catalytic converter for use on factory smokestacks. This consisted of a metal box containing a bunch of porcelain rods over which exhaust gases would flow. These rods, in turn, were coated with aluminium oxide and platinum, the latter of which acted as the catalyst to convert unburned hydrocarbons and carbon monoxide into water and carbon dioxide. He later developed a smaller version, the catalytic muffler, for use in automobile exhaust systems, for which he was awarded the Society of Chemical Industry's prestigious Perkin Medal. An amazingly written 1955 article in Popular Mechanics breathlessly explained to readers just how clever this new device was. A catalyst is like a heckler who prods two other guys to fight. A cat never does much fighting himself, he's needed to keep things stirred up. In your car's exhaust pipe, the trouble is that nobody wants to fight. The waste hydrocarbons and carbon monoxide coming down from your engine aren't hot enough to mix up with the oxygen. In other words, burn. Like snakes on a cold day, they are too lazy to fight. So, Udry throws in a cat and wham, a fight starts. Oxygen from the air leaps with a snarl at the smelly stuff. While the cats glow with the heat of the fight, oxygen rips the hydrocarbons apart. The hydrogen joins some of the oxygen to form water, H2O, and the widowed carbon is swallowed by other oxygen, burning into harmless carbon dioxide, or CO2. Deadly carbon monoxide, CO, gets the business too. Attacked by oxygen, it also burns to CO2. And who said science writing had to be dull? Udry was particularly proud of his creation, boasting, "Put them on all cars and watch the lung cancer curve dip." Unfortunately, this was not to be, at least not in Udry's lifetime. For one thing, public concern over air pollution was nowhere near intense enough to convince automotive companies to adopt such a new, potentially expensive device. But there was an even bigger and more practical problem. At the time, gasoline contained tetraethyl lead to boost its octane rating and prevent engine knocking, and lead residue in the exhaust tended to coat or poison the catalyst, rendering the catalytic converter useless after only a year or two of regular driving. Consequently, Udry turned away from regular automobiles and instead began developing catalytic converters for forklifts and mining machinery used in confined spaces where carbon monoxide levels could quickly build up to lethal levels. Such machinery typically ran on low-grade, unleaded fuel, eliminating the catalyst poisoning problem. Eugene Udry died in 1962 at the age of 70, his dream of curbing automobile emissions unrealized. However, that same year saw the publication of Silent Spring, Rachel Carson's classic expose of the dangers of synthetic pesticides like DDT. This book helped launch the modern environmental movement, which by the late 1960s had grown so large and influential that politicians and industry were forced to take notice. By 1969, smoke over Detroit, Los Angeles, and other cities had gotten so bad that residents sometimes couldn't see the sun at noon, parents were wary of letting their children play outside, and buildings had to be repainted every few years. This crisis spurred the government of then California Governor Ronald Reagan to pass sweeping state emission regulations. The federal government quickly followed suit, and on January 1st, 1970, President Richard Nixon signed the National Environmental Policy Act. Less than a year later, he established the Environmental Protection Agency, or EPA, whose first administrator, Assistant Attorney General William D. Ruckelshaus, immediately ordered the mayors of the heavily polluted cities of Cleveland, Atlanta, and Detroit to clean up their waterways within 6 months or face legal action. And before the year was out, President Nixon signed a massive expansion to the 1963 Clean Air Act, which set national standards for automobile emissions. Specifically, it called for automobile manufacturers and oil companies to reduce exhaust emissions, particularly smog-causing nitrogen oxides, by 90% and to eliminate leaded gasoline from all major service stations by 1975. As you might imagine, that didn't go down well with automakers. The government had just thrown down what science writer Tim Palooka once called a gauntlet similar in spirit to President John F. Kennedy's 1961 challenge to put a man on the moon before the end of the decade. Both were bold strokes that placed a burden squarely on the shoulders of the nation's scientists and engineers, and both looked impossible. Indeed, in order to get cleaner cars rolling off the assembly line by the 1975 model year, manufacturers would have to complete the necessary research and development work within only 2 to 3 years, an absurdly short turnaround for technology that nobody even knew was possible. Ernest Starkman, vice president in charge of the environmental activities staff of General Motors, balked that, quote, "The cleaner the car is from a pollution standpoint, the harder it is to make it run well." While then Ford President Lee Iacocca claimed that to comply with the regulations, the auto industry would have to flat out stop producing cars for several years, saying, "No matter how much we spend and how many people we assign to the task, we do not think we can do it by January 1st, 1975. Under this bill, we would be directly directed to reduce all emissions by 90%, even if nobody knows how to reduce emissions by 90%. But the EPA refused to back down, forcing the Big Four in Detroit to attempt the impossible. Even EPA Administrator William Ruckelshaus later admitted that the Clean Air Act was overly ambitious, stating in 1985 that "we thought we had technologies that could control pollutants, keeping them below threshold levels at a reasonable cost, and that the only things missing in the equation were national standards and a strong enforcement effort." All of the nation's early environmental laws reflected these assumptions, and every one of these assumptions is wrong. With the clock ticking, the automakers decided to tackle the problem of emissions on two fronts. At the source, using improved carburetors, pre-combustion chambers, and dual spark plugs to promote more complete combustion of the fuel, and at the exhaust end, using catalytic converters to clean up any remaining emissions. At first, most research focused on pre-combustion emission reduction. As Rodney Bagley, an engineer at Corning Glassworks, later recalled, hanging a chemical reactor under a car was not something the auto companies wanted to do. They thought that it would be a short-term stopgap until they could design an engine that would reduce emissions using a pre-combustion chamber or some other gizmo. In the decades since Eugene Oudry's death, catalytic converter technology had advanced significantly, with companies like Corning in New York, 3M in Minnesota, and Engelhard Industries in New Jersey all developing more sophisticated alternatives to Oudry's porcelain rod design. However, all were stymied by the same lead poisoning issue, which would have forced motorists to change their converters, or at the very least the catalyst within, every year. However, the 1970 Clean Air Act's requirement that leaded gasoline be eliminated by 1975 suddenly made these designs feasible. The first company to develop a production catalytic converter was GM, which at the time was not only the world's largest automaker, but also its single largest employer. After assigning over 5,000 workers to the task, including former DuPont chemist Richard Klimisch, GM came up with a pelletized catalytic converter containing hundreds of aluminium oxide beads coated in platinum and palladium catalysts. While GM had tested dozens of cheaper metals like copper and iron, these were unable to withstand high exhaust temperatures. According to GM promotional material, each converter used less than a tenth of a troy ounce, that's around 3 grams of catalyst, yet was able to reduce tailpipe hydrocarbon and carbon monoxide emissions by over 90%. Furthermore, thanks to modifications made on the combustion ends, the new converter-equipped GM models achieved 15% more miles per gallon than their predecessors, proving that Ernest Starkman's concerns about cleaner cars being less efficient were entirely unfounded. To ensure that drivers didn't destroy their catalytic converters, 1975 GM models featured a smaller gas-filling port that wouldn't fit older leaded gas nozzles. But while several other companies like AMC and Toyota opted to license GM's pelletized catalytic converter, the design was soon found to be fundamentally flawed. For one thing, vibration caused the pellets to grind against each other and gradually wore off the catalyst coating, eventually rendering the converter useless. Worse still, carbureted engines tended to swing wildly between lean and rich combustion, resulting in high exhaust temperatures that could melt the catalytic converter. And while GM marketing had boasted that with their design, drivers need to only replace the pellets and not the whole converter, in reality, drivers were unwilling to pay for this kind of regular maintenance, and GM was forced to look for alternative designs. Meanwhile, Ford and Chrysler opted for more sophisticated designs developed by 3M, Engelhard Industries, and Corning Glassworks. 3M and Engelhard had developed a ceramic material made of zirconia and mullite, which could be extruded into corrugated sheets and rolled into a cylinder, creating a monolithic honeycomb structure with a huge internal surface area that would not wear down over time, like GM's pelletized converter. Corning's design, however, was even more sophisticated. Corning had experimented with dozens of methods for producing a strong, stable honeycomb substrate, such as rolling up sheets with glass nibs or ridges to separate them, stacking together circular or triangular tubes, or extruding thin aluminum noodles into something resembling a bird's nest. However, all of these turned out to be too expensive to manufacture or fragile to stand up to regular road use. It was then that engineer Rodney Bagley hit upon an elegant solution. Why not extrude the substance through a die, creating a tough, monolithic honeycomb with thousands of tiny channels running front to back? While simple in concept, implementing this process proved to be a major engineering challenge. If the die wasn't designed exactly right, or the ceramic formulated just so, the tiny channels would immediately collapse after extrusion, like, as Bagley put it, a wet newspaper. The wrong ceramic would also expand and warp when exposed to the heat of an automobile's exhaust, causing it to clog up and disintegrate. However, after months of feverish work and 100-hour weeks, Bagley and his colleague developed a practical extrusion process and a substrate material composed of methyl cellulose and synthetic cordierite, a mixture of talc, aluminium, silicate, and aluminium oxide. This yielded a stable, solid honeycomb structure with walls as thin as 0.02 of an inch or 0.05 millimeters. On November 9th, 1971, the Corning team filed a patent for their design, which was finally granted in February 1974. But Corning wasn't out of the woods yet. With the 1975 deadline fast approaching, they would have to build a catalytic converter factory before their converter design was even finalized. It was a huge gamble, but a necessary one. Not only did Corning stand to reap a $100 million windfall in catalytic converter sales if their design reached the market first, but the fate of the American automotive industry now rested in their hands. If they failed, Ford, Chrysler, and other companies would effectively be forced to shut down until an effective catalytic converter could be developed. In the end, the race to the 1975 deadline proved to be a close-run thing. In June 1975, a massive flood severely delayed construction at the new factory site in Irwin, New York, while in 1973, Corning was hit by a triple whammy of technical issues. Prototype converters kept shaking loose on the test track, problems with the crystal structure of the cordierite substrate caused the honeycombs to warp, and, most worryingly of all, the EPA made a disturbing discovery. Catalytic converters would combine sulfur contaminants from gasoline with hydrogen and oxygen to form sulfuric acid. As one Corning engineer recalled, "I had two elements of the agency pitted against each other. The mobile source people were basically engineers, and the other side of the coin were represented by the health scientists." The latter group argued that catalytic converters would emit a fine aerosol of sulfuric acid, so that anyone standing alongside a Los Angeles freeway would essentially be inhaling a sulfuric acid mist, which was extremely damaging to health. This was a very tough decision to make. I came down on the side of the catalytic converter, which in hindsight seems to have been the right decision. Indeed, testing revealed that sulfuric acid emissions were not a major hazard, and the project was pulled back from the brink of failure. The other issues were also eventually worked out, and by the time the 1975 model year rolled around, the big four automakers had done the impossible, meeting the EPA's stringent guidelines in less than 5 years. It was a spectacular achievement and one of the greatest feats of industrial research and development in history. As Rodney Bagley later recalled, having a major breakthrough is very rare in any company. In the catalytic converter, we had two major breakthroughs: a new process and new materials that didn't exist before. For his historic role in reducing global emissions, in 2002, Bagley, along with his colleagues Erwin Lachlan and Ronald Lewis, were inducted into the National Inventors Hall of Fame. Yet, despite this triumph, automakers resented the government meddling in their business and expended considerable effort trying to paint catalytic converters as a useless passing fad. Indeed, Alan Loughborough, vice president of engineering at Chrysler, called the catalytic converter the dumbest thing to ever happen to the automobile, while today it is suspected that the reason GM held on to its problematic pelletized design for so long was to give catalytic converters as a whole a bad name. Other companies found ways of getting around the regulations altogether. For example, since the Clean Air Act mandated catalytic converters for all vehicles under £6,000, in 1975, Ford introduced its new model, its F-Series of pickup trucks that was just slightly heavier than the cutoff. Known as the F-150, it remains the best-selling pickup truck in the United States. Yet despite this grumbling, the EPA held firm, and by the end of the 1970s, catalytic converters became standard equipment on nearly all consumer vehicles. But there was still plenty of work to be done. The first generation of catalytic converters were so-called two-way models, which did nothing to reduce the nitrogen oxides responsible for the petrochemical smog. The EPA had removed NOx standards from its 1975 requirements to allow manufacturers to focus on reducing carbon dioxide and hydrocarbon emissions, but was due to reintroduce them for the 1976 model year. However, the EPA extended the deadline to 1978, while in 1977 it extended it again to 1981. This time, it was Engelhard Industries of New Jersey who provided the necessary breakthrough. Converting nitrogen oxides to plain nitrogen requires a reduction rather than an oxidization reaction, and Engelhard discovered that rhodium, another member of the platinum group of metals, efficiently catalyzed this reaction. Engelhard's first design was a two-stage system, with one converter oxidizing carbon monoxide and hydrocarbons, and another reducing nitrogen oxides. This system, however, was bulky, heavy, and expensive, and certain to prove unpopular with auto manufacturers. It was then that Engelhard chemists John Mooney and Carl Keith came up with an ingenious solution: adding cerium oxide, which would either release or store oxygen by switching between its CeO2 and Ce2O3 forms. This breakthrough allowed both oxidation and reduction to take place within the same catalytic converter. Introduced in 1973, such three-way converters soon became standard across the automotive industry and remain in use to this day. In 2001, Keith and Mooney were awarded the prestigious Walter Alstrom Engineering Prize for their invention. Modern three-way converters can remove up to 98% of toxic pollutants from a vehicle's exhaust and are estimated to have kept some 800 million tons of pollutants out of the atmosphere since the 1970s. While the basic design of catalytic converters has changed relatively little over the last 50 years, they have benefited greatly from other advances in vehicle design, such as oxygen sensors and fuel injection systems, which allow engines to run at an optimum ratio, that is, neither too rich nor too lean, reducing emissions as the source and allowing catalytic converters to operate at peak efficiency. Yet despite 50 years of development, problems still remain. For example, catalytic converters must reach a certain temperature to operate efficiently, meaning vehicles tend to emit larger amounts of pollutants in the first few minutes after startup, especially in cold climates. Manufacturers have come up with several solutions for this problem, including placing the converter close to the engine exhaust manifold, adding electrical heaters, or installing a smaller pre-cat ahead of the main converter, all of which significantly reduce the converter's warm-up time and overall emissions. And while lead has been eliminated from gasoline, catalytic converters can still be poisoned by sulfur, phosphorus, and manganese found in gasoline and other fuel additives. However, the reduction or elimination of sulfur and most phosphorus from gasoline blends has largely eliminated this problem. But the biggest problem with catalytic converters is the very materials which make their alchemy possible, the precious metals platinum, palladium, and rhodium. Indeed, these metals were the focus of great controversy surrounding the initial adoption of catalytic converters, for in the 1970s, most of the world's reserves came from the Soviet Union and apartheid South Africa. Today, catalytic converters account for 40% of the world's demand for platinum, 70% of the demand for palladium, and 80% of the demand for rhodium, with the global automotive industry spending more than $40 billion every year on these metals alone. In recent years, growing demands for emission control, especially in China, has caused the prices of these metals to skyrocket and caused the price of platinum to skyrocket from $800 an ounce in 1986 to nearly $1,400 today. Similarly, the price of palladium has quintupled to $2,875 an ounce, and rhodium to an eye-watering $21,900 an ounce, around 12 times the price of gold. This, in turn, has made catalytic converters a tempting target for petty thieves, with unscrupulous scrap metal dealers paying anywhere from $150 up to $500 for a single unit. In 2022, more than 64,000 catalytic converters were stolen in the US alone, sticking the vehicle's owners with repair bills often in excess of $2,000. The most commonly targeted vehicles are those with high wheelbases, like pickup trucks and SUVs, since they are the easiest for thieves to slip under, though hybrid vehicles like the Toyota Prius are also popular targets. This is because their engines run less often than regular vehicles, meaning their converters are often in better condition. As electric vehicles become increasingly popular, demand for catalytic converters and their theft may eventually taper off. Until then, however, these ingenious devices will continue to play a vital, if often overlooked, role in keeping our air clean and breathable. So for now, well, just be careful where you park your car.